Okay, welcome back to another video lecture from Math 1316, Trigonometry. And in this video lecture, we're going to be covering sections 4.1, which is the beginning on a unit on graphing the circular functions, which are the trigonometric functions, sine, cosine, tangent, secant, cosecant, and cotangent. Okay, so to begin with, the unit on graphing is very similar to the unit from college algebra, where we learn about the parent functions of the different algebraic functions, like linear, quadratic, cubic, cube root, square root, those types of things. The difference here is that we're now dealing with trigonometric functions or circular functions. In other words, these are what we like to call periodic functions. And by periodic functions, what I mean is that these types of functions repeat themselves over and over and over again. In other words, the values will repeat because they are determined by where on the unit circle we are referring to. So the angle that we give as an input to this function is a specific angle on the unit circle. And so as the angles go larger than 360, by our definition of coterminal angle, we know that they correspond to a different angle between 0 and 360. And so, of course, the sine of 30 degrees is the same as the sine of 390 degrees. And you know that we can add 360 over and over again. So we expect it to hit the same value of the sine of 30 um, multiple times throughout the course of the domain of the function. Okay, so again, this is a whole lot of memorizing. So I just have a graph here on Desmos that we're going to kind of mess with and see what the different parts of the function do and how it is that we can manipulate these things to determine the different properties of the function, such as the zeros, which is the x-intercepts, the y-intercept, the period, and then the general shape of the graph. So here we have a sine wave, and in general, all of these trig functions are determined by four constants, a, b, c, and d, where a determines the amplitude of the function, b is a constant that will determine the period of the function based on how often that function repeats itself. C is a left and right shift. This is sometimes called phase shift, and D is an up and down shift of that graph. Okay, so to begin with, let's just experiment with what happens when I move the A value up and down. So notice that by default, the sine wave begins, and when I say begins, I'm kind of referring to this as the origin is my reference point here. So this 0, 0 point that I've put on the graph. And when I click that, you'll notice that a lot of the key points that we recognize off of our unit circle appear on this graph as we move from left to right. So when I highlight this point, we notice that 0, 0 is a point that sine will pass through, because on the unit circle, when I'm at angle 0, the value of sine is in fact 0. Now, next we notice that as I start rotating around the outside of the unit circle, say all the way up to 90 degrees, well, 90 degrees has the measure of pi over 2 in radians. And we know that when we're sitting at an angle of pi over 2, then the value of sine is 1. And we know that the value of sine, the maximum that it will ever get to is 1. And that's just when we have a angle on the unit circle. Now, we will have bigger values than 1 appearing on the graphs of circular functions, but that is completely dependent upon the radius of the circle. So if we recall, the way that we can define cosine from a previous unit is r cosine of theta is equal to the x coordinate and r sine of theta is equal to the y coordinate. So if I have a bigger circle with radius 2, then the sine wave is expected to go to 2. So if you keep your eye on this point, this is pi over 2 comma 1, and I increase the a value, effectively what I have done here, if I highlight this point again, this is pi over 2 comma 2. So what the a value secretly does, it is the amplitude of the sine wave, or in other words, it is how high up from the midline that the sine wave goes. And it is also referring to the radius of the circle that this sine wave is generated off of. So this is a circle with radius 2. When we are at 90 degrees, the value of sine will be 2. When we have a circle with radius 3, all I have to do is drag this A up, and you can see that I've put it at 3, and so now this is a circle with radius 3, so the maximum value sine will go to is 3 when we are at pi over 2 or 90 degrees. So after 90 degrees, we rotate back down to 180. Notice that this goes back to 0, and then we'll have a negative value on the opposite end of the spectrum. That's at 3 pi over 2 or 270 degrees. So the top and bottom of the sine wave are always the same absolute value. The only difference will be that we have this peak, which is a positive number, and a trough, which is a negative number. Okay, furthermore, it's worth noting that with sine waves, we have what's called a midline. In other words, if you look in the dead middle here, we have 0, 0, which is the default starting place for all sine waves, and it will go down to 0 again at pi, and it will go up to 0 again at 2 pi. So from 0 to 2 pi, you will notice that we have one full peak and one full trough returning to the midline. Now, this is called a period of the sine function because after that point, after 2 pi, if you look again after where the cursor is, um, it's just repeating this same kind of funny S shape over and over again, all the way out to infinity. And it's also worth noting here, if I drag the graph to the left, that it does the same thing on the left as well. So it's just this same S-shaped form repeated over and over and over again um, to to create our sine wave. All right, so the period on a sine wave is from the first place where the sine wave is 0 to, we skip one, the third place where the sine wave is 0. So basically, you find the zeros on a sine wave. There's one, or effectively, where is the sine wave at the midline? And we skip the next place and we go to the third place, basically every odd numbered place here. So that's the first, third, and fifth. Um, from first to third is one period, from third to fifth is another period, from fifth to seventh will be a period, and so on. And the length along the x-axis that it takes to complete that cycle is what we define to be the period. Okay, so I'm going to reset this to radius 1 so that what we are dealing with is a unit circle. And I'm going to zoom in on this first period here. Put my points on. There you go. You can see the little gray dots are the points. Okay, so then we have these other three constants. Now, B is perhaps one of the more complicated constants here because you notice that in the function that is highlighted at the very top line of Desmos here, we have B, and then B is distributed over X and C inside of the sine operator. So B, when it is factored out like this, gives us what the period of our sine wave is supposed to be. If I increase B, let me try to make it 2, then you notice that the sine wave completes its cycle much faster. So this used to go up to 1 about halfway to 2, and then it goes back to normal back to a 0 point where it starts over when we were at 6.28, which is precisely 2 pi. Excuse me. Another way to think about what b does, it controls the period, and the way that it controls it is through the formula 2 pi over b. So if I go down here to a new line and I compute 2 pi over, right now our b is 2, well, then it tells us that our period is pi. So 1 pi as opposed to 2 pi, which is the norm. Now, if I set b back to 1, try to do it here. Okay, set b back to 1, then you notice that the formula 2 pi over 1 will just give us 2 pi. In other words, it completes one full cycle in precisely 6.28, which is 2 pi. So you can, another way to think about what b does, if I move this to 2, you will notice that in 2 pi distance along the x-axis, I can count the number of full periods of sine that I see. So there's one full period, two full periods within 2 pi. So B kind of tells me how many full periods of sine fit within 2 pi of distance along the x-axis. So just to kind of illustrate this a little bit more, let's go to 3. We can count the number of periods. Okay, here's the first place where it's 0. So we skip one, we go to the next, that's one full period. We skip one, we go to the next, that's two full periods. We skip one, we go to the next, you'll notice that we are at 2 pi worth of distance along the x-axis and that there are 3 full periods of sine within that distance. That is the effect that b has on these functions. All right, so I'm going to set this back to 1. This is a normal sine wave. Let's talk about what c does now. So c is a value that controls the shift of this particular type of function. So keep your eye on this 0, 0 point. When I start to move the c value, you notice when I move it pi, so it says minus pi, the effect that it has is the original starting point, the original 0, has actually gone to the right by pi. So effectively what I have in front of me now is a negative sine function, and that's because a 180-degree phase shift to the right is the same as a reflection of sine across the x-axis. So you can see as I move this slider to the left, it moves the graph to the left. Basically, if I have x plus something, you see I'm in the negatives now. If I have x plus something, it moves the graph to the left by that amount. And if I move the slider to the right, all the positive numbers here move the graph to the right. Okay. By default, the sine function that we have dealt with up to this point has a c of 0, and you can see that that matches very well with the parent function for sine. All right, lastly, we have d. So D is really, really simple. If you keep your eye on this midline, now you notice that there's a high point and there's a low point, and then there's all these little dots along the dead middle of the sine graph. That is what we call the midline, and by default on a sine wave, the midline is the x-axis. When I start applying a value to D, like 1, you see that the midline itself gets shifted up, and by extension, the sine wave gets shifted up by 1 unit. So the new midline is now y equal to 1. If I set it to 2, the new midline is now y equal to 2, y equal to 3, y equal to 4, and this matches very well with what we know about vertical shift from like a college algebra class. Okay, so that's basically what all of the different values A, B, C, and D do on the sine function. And it's worth remembering what all of those values control, because the reality is, if you remembered, all of your trig ratios can be assembled out of sines and cosines. And so you notice that if these values control these things on the sine graph, then they must control the same sorts of things on the other trig function graphs. So just to verify that that is in fact true, we're going to now look at the cosine graph. So the difference between a sine graph and a cosine graph, and I want to zoom out, you'll notice they look almost exactly the same. Like it's just this wave pattern over and over and over again. The difference that you need to take note of is when I talk about the starting point, remember that it's always kind of in relation to where the origin is. So sine passes through the origin by default. In other words, its parent function always passes through the origin, and then it begins by increasing. Cosine, on the other hand, if you think about your unit circle, when we go to the unit circle position 0 degrees or 0 radians, it starts at a value of 1. And then as I increase to 90 degrees, you notice that at 90 degrees, the cosine takes a value of 0. So that means that this wave function has to decrease from 1 to 0 within the first 90 degrees. And then as we proceed around the unit circle to 180 degrees, it eventually has to hit -1 down here at the bottom. It looks like my cursor has covered this up, but it's pi comma -1 down there at the bottom. And then it has to process back to 0 at 270 degrees and back to the top at 360 degrees. So one period, again, fits within 2 pi the same as it does with sine. Therefore, the function that describes the period for both sine and cosine is 2 pi over this b value from inside of the cosine operator. So let's just make sure that A does the same thing. Remember, when I move A, what I'm expecting is that it changes the radius of the circle, meaning that the peaks will get larger and the troughs will get smaller. So that means that the moving it to 2, I should go from +2 to -2. From 3, +3 to -3. It basically just controls how high and how low this wave is going to go. All right, remember B controls how many periods I see within 2 pi. So if I put this on 3, then from peak to peak, which is what a period of cosine looks like, you notice that this peak goes to this peak, and then it just repeats that kind of U shape over and over again. From peak to peak, I should have 1 period, 2 periods, 3 periods within 2 pi. I'm at 2 pi on the x-axis, and my b value is 3. That means I should see 3 full periods of cosine within that amount of distance along the x-axis. Now, if I wanted to compute the actual period for this, remember that it follows the formula 2 pi divided by whatever the b value is. So this is 2.09, which is just 2 pi over 3. Now, to verify that, we can go to this first completed period, and we see the first completed period happens after 2 pi over 3, and that matches with what we know about the b value and what it controls. So C, if you remember, positive numbers will move this graph to the left because the function will now say x minus a certain positive number, and negative values will move the graph to the left because it now says x plus a certain number. And that matches very well with what we know about functional transformations from college algebra. Basically, x minus something moved the graph to the right, and x plus something moved the graph to the left. And then D will very easily control the midline the same way that it did before. Remember, the midline is just this spot right in the middle that keeps repeating over and over again more frequently than the peaks and troughs. Or at least it looks more free. It's not that it's actually more frequently; it's that it looks more frequently. So if I move this value of D, it moves the physical midline up and down, and therefore the entire graph moves up and down. Okay. So some other things to notice as I zoom out on this thing, what you'll notice, since it just repeats itself over and over and over again, I'm now out to -100, +100. What you'll see is that the graph never stops. Like there's no breaks in this line. So that gives us a couple of the key features of sine and cosine. First of all, the domain for both sine and cosine is all real numbers. But you'll also notice that the graph is limited in the sense that it only ever bounces between the amplitude numbers So if the amplitude is 1, it only ever bounces between positive 1 and negative 1. It does pass through 0, but like we have up to positive 1 and down to negative 1. So the way that we write that interval for the range will be a square bracket. Whoops. Undo that. The way that we write that is a square bracket from negative 1 to positive 1, and that is the interval for the range for both the sine and the cosine value because they just oscillate between these two. If I increase the amplitude to 2, well, then the range would be negative 2 to positive 2, and so on. If I apply a shift to the graph, so like d equal to 1, then all that's going to do is increase both numbers by 1. So this will be negative 1 to positive 3, and you see that that very easily tells us what the range is. The domain will be all real numbers, so regardless of what the value of c is, it will always be all real numbers on both sine and cosine. Other things that we want to notice here, these are some properties that we'll go into more detail during class about, but the cosine graph is considered to be an even function because it has reflectional symmetry about the y-axis, and the sine function is considered to be odd because it has rotational symmetry about the origin. In other words, the sine of negative x is just the same thing as negative sine of x, and the cosine of negative x is just the same thing as the cosine of x. And these are identities that we will go over in some detail on your pink sheet, the identity sheet that's given to you for this class. And most of the homework here will simply be asking you what is the amplitude, so you can look at the value in front of sine or cosine. If you look at the a value, that's the physical position of the amplitude. And then it will also ask you to determine the period. So what is the period? You have to work out what this b is in factorized form. And then after we've worked out what that b happens to be, we just do 2 pi over b, and that states the period. Now, some of the questions a little bit later on, we'll talk about phase shift from left to right, and vertical shift or midline shift from up to down. And we will talk about those in a later section, but I felt that it was important to go ahead and show you the full general form for the trig ratios, sine and cosine. You notice the only thing I had to change in these two things was which trig ratio I used. So if I change this back to sine, I get a sine wave, change it to cosine, I get a cosine wave, and all of the numbers do the exact same thing on both of these trig functions. So if you understand that, then you understand section, I believe this is section, oops, forgot which one it is, that's not good, 4.1.